In this video, I will show how to solve the trigonometric basic equation sin x equals a. I will also include one example, which will be sin x equals 1 over 2, which I will show how to solve in the end of this video.
What you see here is the graph for the periodic function fx equals sin x. If you include a graph for another function which I will define as gx, and that we can say is equal to a certain number a, and then let's say that number a is equal to 0.5, then that graph for that specific function will be this horizontal line here, which is equal to gx equals 0.5. If I find the specific intersection point between these two graphs, fx and gx, the ones which I will indicate here, that will actually be, if you recall from the first semester when we discussed intersection points between two graphs, that will be the points which these two graphs has in common. So if we have the one function gx equals a and another function fx equals sin x, which is the two graphs you can find over here, then the specific intersection points will then be when fx is equal to gx, that is the two function values of the two functions, that is the two y coordinates, must be the same for fx and gx, and since fx is defined as sin x and gx is defined as a, then if I can solve this equation here, the solution will exactly be equal to the intersection point between the two graphs. We see that we do have a restriction to the value of a, because if we should find intersection points between the graph for fx equals sin x and the graph for gx, then gx must be equal to a value which is in between -1 and 1. As you can see, we will never have intersection points if you find a value for gx which is smaller than -1 or greater than 1. If you recall from when we discussed the function fx equals sin x, you can see that we don't have any restrictions to x, so x is a member of all our real numbers. So how do we solve this basic equation sin x equals a? Let's look into one example and then we can generalize afterwards. The example I have chosen to include is to solve sin x equals 1 over 2, and that is an example of this basic equation sin x equals a, here where we see a is equal to 1 over 2, which is okay. A just has to be in between -1 and 1, as we just discussed on the previous slide. We don't have any restrictions to x. X belongs to our real numbers. If we then look into the unit circle, here we have it. Then you hopefully recall that the sine value we'll find on our y-axis. So if we're looking into angles, that is values for x, where the sine value will be equal to 1 over 2, that must be approximately here. So the angle I'm looking for here must be this one here. Exactly this one angle here will give me a sine value which is equal to 1 over 2. But so will also the angle over here. This one here, which recall is equal to pi minus x. So we have two potential solutions here. We have both x, the angle x, and the angle pi minus x. So if we have sin x equals 1 over 2, we can see that x must be equal to inverse sine 1 over 2, or x must be equal to pi minus x, and x we have just indicated is equal to inverse sine 1 over 2. We are almost there. We just need to remember that if we take, if we look at this result here where we have the angle x, which gives me a sine value which is equal to 1 over 2, every time we take a journey around the unit circle, that is, we add 2 pi to our initial x, then we get to another solution, another angle which has a sine value which is equal to 1 over 2. And we can do the same thing if we take another journey around the unit circle. We'll get back to another solution, and so on and so forth. So we have to add in our period p times 2 pi. As we recall, one journey around the unit circle is equal to 2 pi. And p has to belong to our integer, because we need to remember that we need to make a full journey around the unit circle in order to get back to an angle which also has a sine value which is equal to 1 over 2. And the same thing is of course the case with the other solution here. Every time we take a journey of 2 pi, we get back to a new angle which has a sine value which is equal to 1 over 2. So we of course also have to add in our period down here. So now we're almost here. We just need to remember to calculate x equals inverse sine 1 over 2, which is equal to pi divided by 6 plus p times 2 pi, or the other potential solution is pi minus inverse sine, so that will be pi minus pi divided by 6 plus p times 2 pi. So that altogether gives me x equals pi over 6 plus p times 2 pi, or x equals pi minus pi over 6. That leaves me with 5 pi over 6 plus p times 2 pi. And p, of course, as we just agreed, has to be an integer. So that is our total solution to the initial equation sin x equals 1 over 2. Alright, so if we go back, then we see here a general picture. When sin x is equal to a has to be in between minus 1 and 1 in order for sin x equals a to have solutions. Then we find our solutions x to be equal to inverse sine a plus our period p times 2 pi, or x is equal to pi minus inverse sine a plus p times 2 pi. So that's generally how we solve our basic equation sin x equals a. Look into the next video if you want to videos if you want to figure out how to solve the basic equation cosine x equals a and tangent x equals a.